my last lecture, I started to discuss semiconductor materials. So I discussed what is intrinsic semiconductor, what is extrinsic semiconductor. Intrinsic semiconductor is a pure semiconductor where number of concentration of electrons that is equal to concentration of holes. Whereas extrinsic semiconductor, we are adding some impurity elements to the pure semiconductor, so that is not pure. And this condition is not suitable for the extrinsic semiconductor. The number of holes not equal to number of electrons. So here the thing is we have to find out the carrier concentration in intrinsic semiconductor. That means carrier concentration means number of electrons, number of holes in the intrinsic semiconductor. Similarly, you need to find out the carrier concentration in extrinsic semiconductor. So today I'm going to discuss these all. So today we will discuss first intrinsic carrier concentration. To find out the intrinsic carrier concentration, we must know the density of electrons, density of holes, and Fermi energy. Okay. So first, we will define density of electrons, density of holes. Here, the electrical conductivity of semiconductor depends on the number of charge carriers in thermal equilibrium. So what's that? The electrical conductivity is solely depends on number of charge carriers. So density of states per unit volume in the conduction band. In the conduction band is given. There are three bands now. This is conduction band. And this is valence band. So electrons somewhere here. Somewhere here now. So density of electrons in the conduction band is given by 1 over 2 pi square 2 me star over h cross square 3 by 2 E minus Eg to the power of half. E minus Eg to the power of half. This is your Eg. So E minus Eg to the power of half. Density of states per unit volume in the valence band. So density of holes. Density of holes in the valence band is given by 1 over 2 pi square 2 mh square, mh star over h cross square 3 by 2 minus E to the power of half. Okay. So these two equations very, very important in order to find out the concentration of electrons and concentration of holes. Then another thing is that Fermi-Dirac distribution function. Fermi-Dirac distribution function is also varies for the electrons and holes. So Fermi-Dirac distribution function is given by 1 over 1 plus exponential E minus EF over KT. E minus EF over KT. For electron, E minus EF very much greater than KT. We are considering this condition. E minus EF very much greater than KT. Then Fe is equal to this term. Is very much greater than KT. So 1 plus means this term is very much higher than 1. So you can omit this 1. So you can take this upside. So exponential of minus time E minus EF over KT. That is Fermi function of electrons. So, if you know the Fermi function of electrons, you can find out Fermi function of holes. So, Fermi function of electrons plus Fermi function of holes, that is equal to 1 because it is actually a probability. So, FHE that is equal to 1 minus FEE. 1 minus FEE. FEE is 1 over 1 plus exponential of E minus EF over KT. So FHE is, you can solve this and you will get this formula. But in the valence band, because you are talking about holes, no? So in the valence band, the condition is E less than EF. E less than EF means this term E less than EF. This term become negative. If this term become negative, when you take upside, this term become positive. So exponential of E minus EF over KT very much less than 1. So this term very much less than 1, if this term very much less than 1, you can omit this term and the FHE is exponential of E minus EF over KT. Exponential of E minus EF over KT. So these derivations are important, okay? First, you need to find out density of electrons, density of holes, and Fermi energy of electrons, Fermi energy of holes. These 4 equations very, very important. Now, we can find out easily density of conduction electrons. So, density of electrons, this formula is given by this. And Fermi energy is this. So, how to find? This is the formula. So, the total number of conduction electron per unit volume, that is equal to N is equal to Eg to infinitive. Eg to infinitive. Please consider the limit here. This is your limit. Eg to infinitive here. Eg to infinitive. So, density of electrons Fe into dE. So, you have to apply 1 over 2 pi squared. These all are constant. So, you can take the constants out. 1 over 2 pi squared, 2 me star over h cross squared, 3 by 2. Here, integration. See this integration. This EF over KT also constant. EF over KT is also constant. So, you can take this out. See this integration. So, integration Eg to infinitive, E minus Eg to the power of half, exponential of minus E over KT into dE. So, here, it's very hard, no? It's very hard to integrate because here also you have E, here also you have E. So, it's like UV integration. So, at this condition, you need to change this dE. You need to change this dE in terms of some another parameter. Then only you can easily do the integration. So now, to solve this formula, we are easily taking x is equal to E minus Eg over KT. X is equal to E minus Eg over KT. So, you have to change everything. You have to change E in terms of x. So, first, you need to change the limit. Here, the limit is what? Eg to infinitive. So, when E becomes Eg, then you have to apply here. You have to apply this formula. So, E become Eg. So, when E become Eg, x is equal to 0. Then again, E become infinitive. So, you have to apply here, E become infinitive. Then, x is also become infinitive. So, now, this is our new limit. This is our new limit. Now, we have dE in our equation. No? So, we need to find out dE. So, you have to differentiate this dx. So, when you're differentiating, dx is equal to 1 over kt into dE minus Eg is a constant. So, that is equal to 0. So, 1 over kt into dE. So, dE is equal to kt into dx. So, this is what we want. And there E minus Eg. So, E minus Eg is equal to x into kt. So, E over kt is equal to x plus Eg over kt. Okay. So, what are the things you know here? E minus Eg you need. So E minus Eg x into kt. E over kt is here. So E over kt is x plus Eg over kt. And the limit dE is kt into dx. And x E minus Eg over kt. So you need to apply this all in this integration. So when you apply, you will get this formula. Eg is a constant, so Eg comes out. Kt is a constant, comes out. Here also kt coming out. Then 0 to infinity, root of x exponential of minus x into dx. Root of x exponential of minus x into dx. Here, the standard integral is 0 to infinity root of x exponential of minus x dx. 0 to infinity exponential of minus x beta. So infinity, this should be infinity. So the standard integration is 0 to infinity root of x exponential of minus x dx, that is equal to root of pi by 2. Root of pi by 2. This will be given in your exam. So don't worry, root of pi by 2. But you have to make your equation like this way. So then you have to apply that. When you are applying that, you will get this formula. So NC is equal to 2 times ME star KT over 2 pi H cross squared 3 by 2. NC is equal effective density of states in conduction band. Effective density of states in conduction band. So number of conduction electrons, concentration of electrons in conduction band or number of conduction electron in conduction band is Nc into exponential of minus time Eg minus Ef over Kt. So do you have any doubt for this? This Nc is a constant value. It's known as effective density of states. Now, we will consider concentration of holes in valence band. Concentration of holes in valence band. This is our density of holes equation. This is our Fermi energy equation. We already derived. So what you want to do? You want to apply. You want to apply here. The total number of holes per unit volume in valence band is given by, why this is minus infinity to 0? Why minus infinity to 0? Because valence band starting from 0. 0 minus infinity. This is your valence band region. This is your conduction band region. Sorry, this is your Eg. This is your Eg. And this is your conduction band region. So that's why the conduction band limit is Eg to infinity. Valence band limit is minus infinity to 0. Minus infinity to 0. Always starting from small value to large value. So minus infinity to 0. So minus infinity to 0, dHe, FHE, dE. dHe, FHE, dE. So number of holes, that is equal to minus infinity to 0, 1 over 2 pi squared, 2 mh star over h cross squared 3 by 2 minus E half exponential of E minus Ef over Kt into dE. So P is equal, You have to take all the constants out. So your integration is this. Now what is your work? You have to change this dE in terms of dx. But you can't take the same way. You can't take the x in the same way, but we did in the previous case, conduction electrons. So you have to take in a different way. Let me see. So here you need to take this way. Minus x is equal E over kt. But the previous case is what? X is equal E minus Eg over kt. This is your previous case. But now minus x is equal to E over kt. So you need to take x according to your need only. So when E is equal to 0, E becomes 0 here. E becomes 0, what will happen? E becomes minus infinity, what will happen? That you need to find. E becomes 0, when E becomes 0, x also becomes 0. When E becomes minus infinity, x becomes plus infinity. So you have to apply here minus infinity, minus x is equal minus infinity. So x is equal plus infinity. Then you need dx, no? So dE. So dx is equal to 1 over kt into dE. So dE is equal to minus kt into dx. And minus E you have here. Minus E you have. So minus E is equal x into kt. And here you have E over kt. So you need to take E over kt is equal to minus x. Now what you want to do? Now you need to apply all of this. You need to apply all of this. When you apply, so your E minus infinity, then infinity, you have to put at the particular point, no? Here, the previous case, minus infinity. So minus infinity has been converted to plus infinity. 0 has been converted into 0. And here x into, here see, minus e to the power of half exponential of e over kt. So minus e to the power of half means here x into kt to the power of half exponential of minus x minus kt into dx. So all the constants should be take out. mh star, ef, kt, all the constants should be take out. Infinitive to 0 minus root of x exponential of minus x dx. Here, our standard integral is 0 to infinity root of x exponential of minus x dx. But here the limit is infinitive to 0 minus root of minus x exponential of minus x dx. So what you want to do, if you want to change the limit, you have to multiply by minus. So when you multiply by minus, the limit will be changed 0 to infinity and the integration becomes root of x exponential of minus x dx, which is equal to root of pi by 2. So 1 over 2 pi squared, 2 mh star over h cross squared, 3 by 2 exponential of minus ef over kt to the power of 3 by 2, 0 to infinity root of x exponential of minus x dx, that is equal to root of pi by 2. So you need to apply that. When you apply that, you will get this formula. P is equal to 2 times mh star kt over 2 pi h cross squared 3 by 2 exponential of minus ef over kt. Okay. So 2 mh star kt over 2 pi h cross squared 3 by 2 exponential of minus ef over kt. When you are simplifying this, you will get this. So NV, that is equal to effective density of states in valence band. When you sort it out, you will get P is equal to NV into exponential of minus EF over KT. Minus EF over KT. Now you need to find out the multiplication of NP. Multiplication of NP. So you need to multiply N and P. When you are multiplying, you will get ME star, MH star 3 by 2 exponential of minus EG over KT. EG over KT. Then NP is equal to 4 times KT over 2 pi H cross squared ME star, MH star 3 by 2 exponential of minus EG over KT. NP is equal to Ni squared. So Ni is equal root of NP. Root of NP. Ni is what? Intrinsic carrier concentration. So Ni is this formula. So very simple, don't need to worry about. When you are looking these equations, it maybe seems like that difficult, but there is nothing, you just want to do small mathematics. So NC, NV into exponential of minus EG over KT. And for intrinsic semiconductor, you know this. For intrinsic semiconductor, number of electrons is equal to number of holes, no? Number of electrons is equal to number of holes. So that's why 2 times ME star KT over 2 pi H cross squared 3 by 2. That means you are equating those two formulas. When you are equating, you will get ME star over MH star 3 by 2 exponential of minus EF plus EG minus EF over KT. So, from this formula, what you can do, you can find out the Fermi energy. You can find out the Fermi energy. MH star over ME star to the power of 3 by 2. That is equal to exponential of 2EF minus EG over KT. When you are taking ln both sides, you can eliminate the exponential. So 3 by 2 KT ln mh star over me star, that is equal to 2EF minus EG. So 2EF is equal to EG plus 3 KT by 2 ln mh star over me star. So this is the final formula. So how to find the Fermi energy? To find out the Fermi energy, you have to equate number of electrons, that is equal to number of holes. At T is equal to 0 Kelvin, what will happen? EF is equal to EG by 2. So at T is equal to 0 Kelvin, your Fermi energy, if this is your valence band, this is your conduction band, your Fermi energy at the middle of energy gap when T is equal to 0 Kelvin. But what will happen when you apply the temperature? That may be here, or that may be here, or that may be here. So if you provide more and more energy, Fermi energy shifted. So in intrinsic semiconductor, Fermi level lies just above the half of the energy gap. Fermi level lies just above the half of the energy gap. So that's all for the intrinsic semiconductor. So what we did first, you need to find out the density of electrons in the valence band, density of electrons in the conduction band, density of holes in the valence band, Fermi energy in the conduction band, Fermi energy for the electrons, Fermi energy for the electron, Fermi energy for the holes. Then to find out the concentration of electrons, you need to multiply this, then you will get this formula. Thereafter, to find out the concentration of holes, you need to find out the density of holes in the valence band and the Fermi energy of holes. Then you have to multiply. So then when multiplying, you will get this. Then you can find out the intrinsic carrier concentration, that is Ni, that is equal to root of Np. So you need to multiply N and P. And find out the Fermi energy, you have to equate number of holes is equal to number of electrons. Then intrinsic semiconductor Fermi level lies just above the half of the energy gap. Now we are coming to the extrinsic semiconductor. What is the speciality of extrinsic semiconductor? Number of holes not equal to number of electrons. And there is an extra energy level is created here. For the N-type semiconductor, donor level is created very near to the conduction band. And for the P-type semiconductor, acceptor level is created near to the valence band. So these are the differences between the valence band and, intrinsic semiconductor and extrinsic semiconductor. Now we need to find out the conduction electrons and conduction holes. Concentration of electrons and concentration of holes. So what we can do? So I already explained that electron is because of why? Holes because of the intrinsic carrier concentration plus number of donors. We accept this. Electrons coming from the donor ion, because donor atoms provide the electrons and they will become donor ion, and some of the electrons in the valence band can be going to the conduction band. So the electrons is coming due to the intrinsic semiconductor, or coming due to the electrons jumping from valence band to conduction band, and then number of donors. So here ND be the donors per unit volume. ND be the donors per unit volume. That means concentration of donor atoms occupying the donor level with energy ED. The electron concentration in the conduction band is Nc into exponential of minus Eg minus Ef over Kt. Nc into exponential of minus Eg minus Ef over Kt. This must be equal to sum of concentration of ionized donors, Nd plus in the donor level plus concentration of thermally generated holes in valence band. So the number of electrons that is equal to Nd plus P. But for the N-type material, this is very, very less compared to the donors. So you can neglect only at low temperature. If the temperature is high, the number of holes also become high, so you cannot omit. But at low temperature, you can omit this. So N is equal to Nd plus. So N is equal to Nd plus. So Nd plus is equal to Nd into probability. Nd into probability. Nd plus, that is equal to Nd into 1 minus FED. 1 minus FED. Nd plus is equal to Nd into 1 minus 1 over 1 plus exponential of minus time Ef minus Ed over Kt. What is that? Fermi energy is equal to 1 over exponential of E minus Ef over Kt. E minus Ef over Kt. but we are taking minus out. So that's why EF minus ED over KT. So you are equating, you are doing the mathematical work here, 1 out. So ND plus is equal to ND into this term, but EF minus ED very much greater than KT, very much greater than KT. So this term become a minus term. So minus infinity, EF minus ED very much greater than KT. So this is become very, very larger. So exponential of minus means it's very, very smaller. So you can omit this. So your equation become exponential of minus time EF minus ED over KT. Minus time EF minus ED over KT. ND plus is equal to ND into exponential of minus time EF minus ED over KT. So N is equal to NC into exponential of minus time EG minus EF over KT. N is equal to NC into exponential of minus time EG minus EF over KT. That is equal to ND plus. That is equal to ND plus. This is what? This is because of the intrinsic semiconductor. For the intrinsic semiconductor, this is NC into exponential of minus EG minus EF over KT. We already derived for the previous slides. So you are going to apply this here. N is equal to ND plus now. So we found ND plus and we know N, number of electrons N. So we are equating these two. When you are equating these two, you will get this ND over NC exponential of minus 2EF over KT. Then you have to eliminate this exponential. That's why you have to take ln both sides. So when you are taking ln both sides, you will get this formula EF. What is that? Fermi energy. Fermi energy for the extrinsic N-type material. Extrinsic N-type material. So this equation is only valid for the low temperature, not for the high temperature, because we assume that at the low temperature. So this equation gives the position of Fermi level in N-type semiconductor. This equation is not valid at T is equal 0 Kelvin by T is equal to 0 Kelvin Eg plus Ed by 2. So that is not valid, and this equation not valid for high temperature. At high temperature, thermally generated holes are very high, so we can't neglect holes. We can't neglect holes. According to this equation, Fermi energy lies somewhere near the middle of donor level and edge of the conduction band. Now, we need to find out P-type extrinsic semiconductor. P-type extrinsic semiconductor. For the P-type extrinsic semiconductor, holes due to because of the electrons from intrinsic semiconductor plus donor ions. So when temperature goes up, a part of acceptor is ionized by acquiring electron from valence band, thus creating holes in the valence band. Therefore, it is P-type semiconductor. So carrier concentration is equal to NB into exponential of minus EF over KT, NAB acceptor per unit volume. NAB acceptor per unit volume. So here you know that N can be neglected because it's a P-type semiconductor at low temperature. It is very, very less. So P is equal Na minus. So first you need to find out Na minus. Na minus, that is equal to Na into FEA. So Na minus equal to Na into 1 over exponential of EA minus EF over KT. So Na minus is equal to Na into exponential of minus time Ea minus Ef over Kt, and P is equal to Nv into exponential of minus Ef over Kt. So dear students, you have to equate these two, and can you tell me the Fermi energy? Send me the answers. Do it this and send me the answers. You just want to do the mathematical work. There is no physics. You just want to do the mathematical work and find the Fermi energy, EF. Okay, wait dear, we will check it. 20 PS13. Answer, Na into Na minus equal Na into exponential of minus time Ea minus Ef over Kt. So, Nv into exponential of minus Ef over Kt, that is equal to this. So when you are doing further, you will get this formula, Nv over Na exponential of minus 2 Ef over Kt exponential of minus Ea over Kt. Then when you eliminate exponential, you will get this, ln Na over Ne plus minus Ea over Kt. So Ef is equal to Kt by 2 ln Na over Nv plus Ea by 2. Okay, Ea by 2. So Hall effect, that is not necessary to you. I'm not going to teach Hall effect for you, but it's very simple. The thing is, your course is 1 credit course, but the contents for your course they have included is the 2 credit content. So I can't add all the theory parts for your final exam. I can't cover for all contents for your final exam. So I am thinking to omit this part. That means pre-electron theory and band theory for your final exam. But you will have continuous assessment in this. So you have to study. However, you have to study. I'm going to do the continuous assessment from pre-electron theory and band theory. But for the final exam, you don't need to study free electron theory and band theory. Okay, dear students. Do you want to ask anything for you? Because this is the end of the theory part. And coming Thursday, I'm going to conduct tutorial discussion from solid state physics, not material physics. Thereafter, I will inform you about the continuous assessments. You will have two continuous assessments. One is from the atomic packing friction and other one is from free electron theory and band theory. But the free electron theory and band theory will not be included in the final exam. So you don't need to study for the final exam, but for the continuous assessment, you must study because you don't have any choices for the continuous assessment. You have only two continuous assessments. So do you want to ask anything or do you want any clarification from any parts of the solid state physics? You can ask. I think you don't have anything. So please study this. This is full of mathematics. Actually, I will take around 4 hours to cover today. If you want anything, you can send me.